the binomial expansion, the binomial theorem. So again, I'm going to talk about binomial expansion, but this time I'm going to use the tools that we have developed in the previous two videos, namely the knowledge about the binomial coefficients n choose 1, n choose 0, etc. until n choose n. So here is the formula, which is perhaps rather intimidating at the first sight, but it's the formula for the binomial expansion of a plus b to the power of n. Okay, a plus b to the power of n equals this. So you notice that altogether we have n plus 1 terms in it, as we should according to the knowledge about the binomial expansion. When there is the coefficient of n, the power of n, we should have n plus 1 terms. And this is really so. Each term, each independent term, this is actually the zeroth, or actually the first term, yeah, we could say the first term, this is the second term, this is the r plus 1 term, this is the nth term, and this is the n plus 1th term. We have n plus 1 terms because 0, 1, etc. until n make altogether n plus 1 numbers. Okay, the numbers from 1 to n, there are n of them, but plus this one, so we have n plus 1 numbers, or n plus 1 terms altogether. In each term we have the product of some power of a and some power of b. You see that the powers of a decrease by 1, so n minus 1, n, etc., n minus r, it's the general somewhere in the middle. We have we have 1 here and we have 0, and the powers of b increase by 1, so we have 0 at the start, 1, then there will be 2, etc. This is the power r, etc. There is the power n minus 1 in the penultimate term, and then we have the n in the last term. Moreover, the sum of the coefficients of these powers, the sum of the powers of a and b should be always 1. So n plus 0 is, as you can see, it's n minus 1 plus 1 is also n minus r plus r is again n, 1 plus n minus 1 n is n, 0 plus n is n. So the sum of these powers has to be always the same as the power here, and the coefficients of each of those terms are the combinatorial numbers, or what we call binomial coefficients. And these should be the numbers, according to the first video of this module, these should be the numbers in the nth row of the Pascal's triangle. So you know that the nth row of the Pascal's triangle from the previous video really can be expressed by binomial coefficients like that. Okay, so the general form of the r plus 1 term of the binomial expansion t sub r plus 1 is this. So let me use colors to tell you what I mean. This term somewhere here in the middle is something that we call t sub r plus 1. This is the so-called r plus 1th term. Why? Its name, or its number, depends on this number here, on r. It's r plus 1th. For example, if we take this to be the first term, t1, which can be written as t0 plus 1th, this can be taken as the second term, t2, which can be written as t1 plus 1, so this number 1 is this 1, this 0 is this 0. Then there would be the third term, which would be expressed as t2 plus 1, which means that r would be 2 in it. This one, this term, is the nth term. This is the tn, which can be expressed as tn minus 1 plus 1, and n minus 1 is actually here. Okay, and this one is the tn plus first term. Okay, and you see that this n here is here in the second row of the binomial coefficient. So this formula helps you to calculate or to evaluate the r plus 1th term the general term of the binomial theorem. Okay, so what you can see, the r plus 1th term has the coefficient n choose r, the power of a is n minus r, and the power of b is r, as can be seen here. The sum of the powers, n minus r plus r, is n, as it should be. It should be equal to this number here. And yeah, that's it. It has the correct general form. Now, let me use this crazy formula for some simple example. Imagine I want to evaluate a plus b to the power of 3. Okay? So, according to this formula, the first term should be 3 choose 0 times a to the power of 3, n, times b to the power of 0, plus, this is the first term. This term following this, the first term, is the second term, and it should have 3 choose 1 as the coefficient, times a to the power 1 less than 3, it is 2, times b to the power 1 more than 0, which is 1. So this was the t2, plus the third term should have 3 choose 2, times a to the power 1 less than 2, which is 1, times power b to the power 1 more than 1, which is 2, plus, and well, actually this was the third term, and plus 3 choose 3, so you see the last term, and choose n, times a to the power of 0 times b to the power of 1 more than here, to the power of 3. So this was the fourth term. If I wanted, for example, the third term expressed using this wonderful formula, the third term is the term which can be written as t2 plus 1, and it tells me that r should be taken as 2, and then according to this it should be 3, because n is 3, this is the number n, 3 choose this r, 2, times a to the power of n, which is 3, minus 2, 3 minus r, so 3 minus 2, times b to the power of r, which is 2. And you can see that this is really 3 choose 2 times a to the power of 1 times b to the power of 2. And when you compare it with this one, you see that they are actually the same. So this formula tells you what the power of a and power of b in the r plus 1th term are, and what the coefficient of this term is. Now, the last line of this box mentions something which is called sigma notation. When somebody uses sigma notation, it will enable him or her to write shorter than this. The binomial theorem written in this first line is intimidating, but it can be rewritten in an equivalent way like this. A plus b to the power of n is the sum, so this symbol sigma means the sum from r equals 0 to r equal n of these expressions. So these expressions will vary for each different distinct value of r. You get a different expression. They are varying, but they form the correct formula. So to show you how it works, I will use it for a plus b to the power of 4. A plus b to the power of 4, according to this, should be the sum of r equals 0 to 4 of, and I have n choose r. In my case, n choose r would be 4 choose r. R is variable. For each value of r in this sum, I have different number here, times a to the power of 4 minus r times b to the power of r. So how to work with this sigma notation? It's like, imagine you are a computer and you have the cycle 4. 4 r equals 0 to r equal 4, do the following: add these terms. Okay, so let me take r equals 0. I will write this term, but with r being equal to 0. So it's 4, choose 0, times a to the power of 4 minus 0, which is 4, times b to the power of 0, and plus. Now take the following value of r, number 1. So if r is 1, I will use 4, choose 1, instead of r I write 1, times a to the power of 4 minus 1, which is 3, times b to the power of 1. Okay, plus. Now let me take r equal to 2. Okay, so it's 4, choose 2, times a to the power of 4 minus 2, which is 2, times b to the power of 2. Okay, plus, let me take r equal to 3. So it's going to be 4, choose 3, times a to the power of 4 minus 3, which is 1, times b to the power of 3, because r is 3 in this term, plus, and finally we can have r equal to 4, which is the stopping value. We have to stop there. So it will be 4, choose 4, times a to the power of 4 minus 4, which is 0, times b to the power of 4. And this is the correct binomial distribution, binomial expansion of a plus b to the power of 4. These coefficients are the coefficients of the Pascal's triangle of the fourth row. So this is 1, this should be 4, this should be, as far as I remember, 6, this should be again 4, and this should be 1. So these coefficients are known, and here you have your expansion. Okay, so this is how the sigma notation works, and notice, please notice that this is nothing else than the tr plus 1th term. So we sum up, or we add up all the terms from r equals 0 to r equals 4, and from 0 to 4 you can count it: 0, 1, 2, 3, 4, you have 5 terms altogether. So as you should have it, one more than the power. Power was 4, so we have 5 terms.